Hello, and welcome to a digital statistics lecture for Salt Lake Community College. In this video, we're going to be talking about section 10.3 for Math 1040, hypothesis test for a population mean. I will note right now that we are going to be working with a data table that is located on page 14. If you want to be ready for that, go ahead and go to that and put that into your list. I put that into L1, and it has about 22 values, it looks like, so it has some number of values, so it may take a minute to put in. So go ahead and do that if you have not already done so. In this section, we're going to move on from population proportions and talk about how to set up hypothesis tests for population means instead. Doing so isn't going to change too much, but there's a few things of note. For example, when we're talking about our conditions we need to check for normality, we still need to look for simple random samples. We still want to check to see if the sample size is less than 5% of the population, which is our independent criterion. And what we also want to show is the central limit theorem right here. We want to make sure that either we have that it is a normally distributed population, or, which we usually don't know that, if we don't know that, we want to make sure that the sample size is large enough, or bigger than or equal to 30. Those are the same three conditions we had in Chapter 9 and also Chapter 8, so all of this is coming together. When we analyze the hypotheses we set up, we're either going to have two-tailed, left-tailed, or right-tailed tests, and they'll be set up in the exact same way as they did before. And we'll be finding a level of significance alpha and seeing which is our level, our series system of making type 1 error. If we don't have one, we'll come up with one, try to keep it small. And then we'll compute the p-value and compare that to alpha to see if we should reject or fail to reject the null hypothesis. For all the two-tailed, left-tailed, and right-tailed tests, the value in the middle should be the mu sub 0, the population mean that we have set up in our hypothesis test. And if we're looking at two-tailed, that means we're checking on both sides, these both sides being alpha. If we're looking at left-tailed, that means we're looking at just the left side, that side being alpha. Or if we're on the right side, we're checking the right side, that side being alpha. And then we're going to test to see if our tested mean, if x bar, is either, say, on the right-tailed test, if it is before it, or if it's after it. Either way, if it's before it or if it's after it, the area beyond it will correspond to the p-value. So that is why we check to see if p-value is less than alpha. If it is in that range, if it is less than alpha, then we will still reject the null hypothesis. If it is greater than alpha, that means we fail to reject. So our conclusions will stay the same. So quick overview over everything we did in the last two sections. One other note here, though, is what we call practical significance. And this will particularly show up with population means and sample means. And practical significance is basically the concept of taking a step back from the values that we found and thinking about it if it makes any practical sense to actually present. If there's actually any real reason to show that. For example, maybe if I have that the amount of raisins in a box of Raisin Bran, which is a cereal, and I think that the average amount of raisins in that is about 2 cups. And then I find that after doing some testing, maybe after testing 2,000 boxes, I find that the mean is actually 1.99 cups of raisins. If that ends up being significant, then I'll result and say that there's a statistically significant difference. However, that might not be practically significant depending on the circumstance I'm working with. So taking a step back and thinking, is there really any point to this? Or a best way to think about it, would this be something that you would read in the paper? If this was something that you would read in a paper, then it may be practical. But if it's not, if it doesn't seem relevant at all, it may not have practical significance. A thing that can really lead to that is large sample sizes. So if n gets too big, that can actually muddle the results, which is why we try to keep a balancing act. We want to keep n to be large enough, but not too large, to make sure that our information is still important. So be wary when you have really large sample sizes. That could cause a loss of practical significance. All right. Now, when we work through these, we're going to work through another program. You could do this by hand if you want to, but our program is going to be in the same place. Remember that we did one prob z test for proportions. So stat over in test. We did the fifth option, 1 prob z test, for proportion hypothesis tests. However, here, since we're doing hypothesis tests on a mean, what we're going to do is actually t-test. It'll still be based on the t-statistic, just like the confidence interval for mean was. We use t-interval for that. However, in this case, we're doing a hypothesis test, so we're going to use t-test instead. All right, so a couple examples of that here. A FICO credit score is used by credit agencies to assess the creditworthiness of individuals. Values range from 350 to 850, with FICO score over 700 to be considered a quality credit risk. According to the Fair Isaac Corporation, or FICO, the mean FICO score is 703.5. So that's what they present. That's what they present to be true. That's going to be our mu sub 0. A credit analyst, so probably credit analysis, okay, wondered whether high-income individuals or income in excess of $100,000 per year had higher credit scores than that. He obtained so it should be analyst. He obtained a random sample of 40 high-income, so that's our sample size, so that's a little n here, high-income individuals, and found the sample mean to be 714.2, so that's x bar, with a standard deviation of 83.2. So that's S. No, that's S, not sigma, because it's from a sample. Conduct a hypothesis test at the alpha of 0.05 level significance, so keep that in mind, to determine if high-income individuals have a higher credit score. All right, so what we're going to do is set up through and knock down all this hypothesis testing. However, yet again, we should check our conditions, and these are really easy to do. Shouldn't even need a calculator for it. First, is it random? Well, based on this line right here, says it was a random sample. That's good enough for us. So it is a random sample. Our sample size is 40. That's more than 30, so it's good enough. And also, it's probably small enough. It's 40 high-income individuals. That's probably less than 5% of all high-income individuals. So it meets all three conditions. With all that in mind, we should be able to set up our hypotheses. In this case, we're working with a mean, so mu, and our null hypothesis is that it is equal to what it once was, or what's the original value that the Fair Isaac Corporation reported, 703.5. What we want to see is if they have a higher FICO credit score, so if their value is greater than 703.5. And if we note, our value of 714.2 is above 703.5. However, yet again, our question is going to be, is it significantly higher than that? So that's what we're going to look for. We're going to find this p-value. And we can do so by working through our previous function. Alpha, to find alpha, that was given to us. That's given to us as 0.05. And we can find our test statistic and p-value both by using t-test. If you remember using t-interval back in chapter 8, or chapter 9 for confidence intervals, this is going to work in a similar way. T-test is going to ask a lot of similar questions. First, it'll ask either data or stats. It'll ask data, which means do you have a list of information, or stats, which means do you have the statistics from that information. Here we don't have the actual lists of data. We have the statistics given to us. We have the sample mean, the sample standard deviation, all that's provided. So we should go into stats. Mu sub 0 is 703.5. X bar is our sample mean. That's 714. Should be 0.2, shouldn't it? 0.2, yeah, I think I put 0.5 up here. So 0.2. Our sample standard deviation, that's 83.2. N is 40 individuals. And what we're testing for is mu greater than mu sub 0. That's our alternative hypothesis. So those are all the inputs for t-test. We put those in appropriately, 703.5, 714.2, 83.2, 40, and greater than. We put all that information into t-test and calculate. We get a t-statistic, or a test statistic, of 0.813. Or I'll just say 0.81. Normally we just round these to 2 decimal places. That is really low. That is less than 1 standard deviation away. That does not seem very different from the mean. We're usually looking for at least 2 standard deviations away, particularly when testing against this level of significance. And when we look at our p-value, we confirm that this is not looking very good. We get a p-value of 0.0 or 0.2105. And that p-value is really big. That means it's about a 21% chance of seeing something as extreme or more extreme than what we observed. So finding a sample of 40 people, we had this mean of 714.2. There's about a 21% chance of seeing something like that. That's far too likely. That does not seem unusual enough. And since the p-value is bigger than alpha, that means that we are going to fail to reject our null hypothesis, stating that there is insufficient evidence to claim that, I'll type it here just to have more room, that high income individuals have a higher FICO credit score. All right. So that's how I would try to interpret that. Notice that it does state here as a little bit of a hint when writing these down that you should state the alternative hypothesis is true. Keep in mind with this question and all of them, when we ask you a lot of questions with hypothesis testing, we're very often not going to give you these fill-in-the-blank situations of you pick one of these options and make sure you know what you put here. This is up to you to put down. Make sure that you know how you interpret these. Since p is bigger than alpha, that means we fail to reject the null hypothesis, stating there's not enough evidence to conclude that whatever the alternative hypothesis was supposed to be. So make sure you do know the ordering there. All right. On the next page, we have the t-distribution table if you want to use that. This we used back in Chapter 8 using level of degrees of freedom and however much area is in the right tail. In the previous case, the area in the right tail would have been that alpha level there. And that would allow us to find the t value. So everything that we need. However, we don't really need to use that. We can just use t-test instead and focus more on the analysis. All right, but use that if you so please. All right, on page 13. Just type in 13 here. Okay, on page 13, we have another example here. According to the American Time Use Survey, the typical American spends 154.8 minutes per day watching television. So that is going to be our mu sub 0. I already know that this is mu, not p. I don't see anything about a proportion already. So a survey of 50 internet users, so that's n, results in the time watching television per day of 128.7 minutes, so that's our x bar, with a standard deviation of 46.5, so that's s. Conduct the appropriate tests to determine if internet users spend less time watching television at the alpha 0.05 level of significance. Yet again, we should address our conditions for normality. First, randomness. Doesn't say random, but again, it says survey. Survey usually has the implication of random, but we should still state something along the lines of, as long as that survey was conducted randomly. For the other two conditions, looking at n is 50 internet users. That's more than 30, so we have hit the central limit theorem. That's good. And also 50 internet users is far less than 5% of all internet users, even those that also watch television. So this is definitely okay. We hit all three conditions. Again, as long as that survey was conducted randomly. But that's up to the researchers. For h sub 0 and h1, we're still working with mu. And h sub 0 is going to be that it is equal to the assumed value of 154.8 54.8. The alternative hypothesis, on the other hand, is instead going to look at to see if it is less than that. So see if it is less than 154.8. So that's what we're trying to test. And with our mean of 128.7, that is less than 154.8. So far, so good. We just want to see if that's significantly less or not. Alpha was given to us as 0.05. And we can find our test statistic using t-test. With t-test, we have first mu sub 0. That's going to be the value from our hypothesis test, 154.8. We have then x bar, since we're on stats, we have x bar was 128.7, I think. Yep. 128.7. Our sample standard deviation is given to us, so Sx is given to us as 46.5. It's rather high. Our sample size is 50. It's pretty good. And what we're testing for is mu less than mu sub 0. Notice that mu sub 0 in this statement here should be that same value here. That way it says mu less than 154.8, which is what we have in our alternative hypothesis. All right, so if we set that up appropriately, tests, doing the second option for t-test, we have stats. We have mu is 154.8, 128.7, 46.5, 50, and less than. What we get is a t statistic of negative 3.97. So that's almost 4 standard deviations away. That's really far away. And the p-value that we get agrees with that. We get a p-value of 1.18, but that's 1.18 e negative 4, or 0.000118. So really small value. And with alpha being 0.05, that means that p is definitely less than alpha. That means there's a very small chance that if we were to reject, we run into type 1 error. So everything looks good. We should be safe to reject the null hypothesis. Rejecting the null hypothesis is a big deal, so we need to be really sure if we're going to do the so. So since our p-value is so small, it's so unlikely to see these results if the null hypothesis was true. So we would then reject the null hypothesis, saying that there is enough evidence, or there's sufficient evidence to claim that, what was it? Internet users spend less time watching television. Yeah, so that's what we're looking for. That was in the description of the problem. So I'll just use that as my conclusion statement. That's, I'm having trouble typing that right there. I'll just put it here. That internet users spend less time watching television. All right. So that's our conclusion. All right. Hopefully you're starting to see or get the hang of these hypothesis tests. We have a couple more to do here, and this next one here being one where we have a data table. Ooh. All right. A certain brand of apple juice is supposed to have 64 ounces of juice. So that's the supposed value. That's mu sub 0. Because the penalty for underfilling bottles is severe, the target mean amount of juice is 64.05. Oh, all right. So that's our mu sub 0 now. However, the filling machine is not precise, and the exact amount of juice varies from bottle to bottle. That's probably why they overfill it, because it's better to give people more than less than what they're supposed to get. The quality control manager wishes to verify that the mean amounts of juice in each bottle is 64.05, so that she can be sure that the medicine is not over or underfilling. So not over or underfilling. That's going to give us our indication of direction. We're making sure we're not less than or equal to. Oh, less than or greater than. She randomly selects 22 bottles of juice. Ooh, that's going to be a problem. Measures the contents and obtains the following data. So we have this information here. So I already have this information in my calculator in stat edit. So I already have that in list 1. However, there's something that we need to address here. The 3 things for normality. So first, randomness. It says randomly selected 22 bottles of juice. So good. So far, so good. 22 bottles of juice is probably less than 5% of all bottles of juice, so that's okay. However, 22 is not greater than or equal to 30. So it's not greater than or equal to 30. That means we fail the central limit theorem. We would thusly need to know that the bottles of juice is normally distributed. And looking through here, I don't see anything that says that the distribution is normal. We just have the mean presented here. So that means that we do not have enough information for the central limit theorem. Therefore, we cannot assume that this is going to be a normal distribution. That sucks. That means that any hypothesis test we make is fraudulent, is not really valid. So just keep that in mind, that the hypothesis test that we do here does have a significant problem with it, that we fail the central limit theorem, so technically it's not normally distributed. All right, so keep that in mind. But we're going to move on as if it was okay, just so we have an example of working with this data. All right, so state the hypotheses and draw the sampling distribution. Okay, so for h sub 0, we have mu equal to. And for h1, we're also going to work with mu. For h sub 0, we have mu equal to 64.05. That's the assumed amount of juice in the bottle. So 64.05. However, the alternative hypothesis is that they're neither over or underfilling. So they want to make sure they're not over or under 64.05. So not equal to would be our go-to there. If we draw this distribution, we have 64.05. And we want to make sure they're not over or underfilling at the level of significance of not presented. So we can come up with our own. Okay. Furthermore, if I find what this mean is, I can go into stat, into 1var stats, and run 1var stats on L1 to find what that mean is, just so I can see this here. I get 64.00. So they have a mean of 64.00. And I want to find what this p-value is. Now, notice that it does give us a level of significance. It says, should the assembly line be shut down so the machine can be recalibrated, and we have alpha given to us. So we have alpha is 0.01, which is going to be how much is going to be in each tail, because we're doing a two-tailed test technically. We're checking both over here, and we're checking both over here. So we want to see if 64.00 is past that or not. To do so, we can run t-test. However, in this case, I don't need to save this mean and standard deviation. I simply should be able to go into stat and run t-test and tell it instead to use data. I can say, hey, use data instead. Use mu sub 0 equals 64.05 from my hypothesis test. List is L1. Frequency list is 1 because I do not have a paired frequency list. And what we're looking for is mu not equal to mu sub 0. Those are going to be my 4 inputs here. So 64.05, L1, so second one, and then not equal to. If we run that, we get our t-statistic of negative 4.49. If we remember from the last question, we had almost 4 standard deviations away, and that was an incredibly small p-value. This being even more than that. It's more than 4 standard deviations below the mean. we get an even smaller p-value of 2.01 e negative 4. Or 0.000201. So, an incredibly small value. That is definitely less than alpha of 0.01. P is definitely less than alpha. That means we do have enough information to reject the null hypothesis. There is enough evidence to claim that what they were looking for, which was the machine is either over or under filling. All right. So that means that they would need to go and send somebody. That's why alpha is probably 0.01. We have thusly shown that the machine needs to be recalibrated, that there's a problem here. All right, one more. Now again, if you have not already, please pause the video, try this problem on your own, and see how you do. The manufacturer of a daily dietary supplement claims that its product will help people lose weight. The company obtains a random sample of 950 adult males. So 950, that is our N value here. Aged 20 to 74 who take the supplement and finds their mean weight loss after 8 weeks to be 0.9 pounds. So that is X bar. So we have the stats here with a standard deviation of S. Test the hypothesis that the mean weight loss of 0.9 pounds is significant using 0.01 level significance. All right. First, though, our conditions. It says random, so we're good on that. It has a random sample. N is 950, which is far more than 30, so we're good there. And even though it is rather large, 950 adult males aged 20 to 74, that's likely less than 5% of adult males aged 20 to 74. So all three conditions are met. We have a normal distribution, or something approximately normal. For our hypothesis test, this one's going to be a little bit tricky. The null hypothesis is that mu equals some value. And remember that the null hypothesis is supposed to indicate that there is no change from what was originally true. Well, if we're trying to show that this has a positive amount of weight loss, then the null hypothesis, meaning that no change, would indicate that they have lost 0 pounds. So that's going to be our null hypothesis, is that the amount of weight loss is 0. However, we want to show that 0.9 is more than that. We want to show that the amount of weight loss is actually more than 0 pounds. So that's what we're trying to show. So something akin to the standard normal, with 0 being here, 0.9 being above that, and we're trying to find the p-value associated. Alpha is given to us as 0.01. So 0.01. They want to be really sure that this dietary supplement is actually working before they make more of it. And when plugging this information in, we have t-test, because again, we have a mean. Mu sub 0 is 0 pounds. X bar is 0.9. And S is 7.4, 7.2. N is 950 individuals that we looked at, 950. And we're testing mu greater than mu sub 0. So those should be all of my inputs for t-test. From there, we get the test statistic. Well, if I plug that in, I haven't done that yet. So stat over in test for t-test. We have data, or stats. Make sure we go into stats. Mu sub 0 is 0. X bar is 0.9. S is 7.2. N is 950. And we're looking for greater than. So showing that there is a positive amount of weight loss. We calculate and we get a t-value, or a test statistic, of 3.85, so almost 4 standard deviations away in the positive direction. and then a p-value of 6.9 or 6.23. Always make sure that if it's above 0, you check the n for a scientific notation, which is e to negative 5 in this case, or 0.0000623. That means the p-value is less than alpha, which alpha was 0.01 if you recall. And because it is less than alpha, that means that we reject the null hypothesis because there is enough evidence to show or to conclude that the supplement helps with weight loss. So that would be my conclusion there. All right. So that's what I'm looking for here. See if I can move that. All right, whatever. So that's my conclusion, that the supplement helps with weight loss. We have a couple follow-ups here, though. Do you think the mean weight loss of 0.9 pounds is worth the expense and commitment of a daily dietary supplement? In other words, does the weight loss have any practical significance? Well, if we look at that, the supplement itself was a supplement that they took for 8 weeks. And after 8 weeks, what we've shown is about 1 pound of weight loss. Standard deviation of 7.2, so pretty wide variance there. So I definitely say that no, this does not hold any practical significance, and I'll type that out so I can have more words there. So no, this does not seem to hold any practical significance, as only losing 0.9 pounds on average after 8 weeks of a dietary supplement does not seem worth the commitment. So this is an example where the practical significance comes in, where we take a step back and say, okay, so we showed that it was statistically significant, that it does show a high level of, or it does show that a positive amount of weight loss was influenced on average. However, the amount of weight loss does not really seem that practically significant. This does not seem like something you would read in a newspaper of, this dietary supplement may be helping you lose 1 pound. That doesn't really sound like a good thing to read in a newspaper. Now, as an example of this, it then gives us the chance to then reevaluate this, however, just change the sample size. Instead, change n to be 40 instead of 950. Even looking at that, 950, that should have been a red flag for us, thinking that that seems like a really high sample size, and that could lead to a loss of practical significance. Whoa. So if we run the exact same test, only changing the sample size to just be 40. Note that 40 would still be above 30, so it passes central limit theorem, still passes the independence criterion, so it still would be normally distributed. So it still is okay. If we do that, however, what we get is a p-value of 0.217 about. And that being greater than alpha, which was 0.01. So what do you conclude about the assume the same sample statistic, would the sample mean weight loss of 0.9 pounds be significantly more than 0? No, it would not. And what this is showing is that larger samples can have a really big impact on the statistical significance of a test. If you have too big of a sample, that could muddle the results and make something that does not seem really important or really relevant look statistically significant. So basically making sure that we're not just blinded by statistical results and mathematical results, we also think about what it means practically. But with that said, that's it for 10.3. At this point, I recommend going through and trying your hand at the homework in section 10.3 before moving on into chapter 11. There's also probably a homework on 10.4, but if there is, that's just a recap of everything from chapter 10, so nothing new there. I hope this helped, and I hope that you have a wonderful day.